So I'm going to talk about these hybrid organic-inorganic perovskite halides. So just a sort of overview. I'll just remind everybody, because it's a mixed audience, remind you about the perovskites, both inorganic and hybrids, and then talk a little bit about applying the Goldschmidt tolerance factor to these systems and issues of polymorphism, and then say a few words about the perovskite formates, which we've done a lot of work on, before focusing on the halide systems, and then look at some of the future challenges in the area. So if you think of the perovskite structure, most people will be familiar with the inorganic perovskites like calcium titanate or barium titanate, and these are the kind of workhorse of condensed matter physics, providing ferroelectrics and high TC cuprates and multi-ferroic materials, giant magnetoresistance, and so on. Over the last few years, there's been an evolution to hybrid systems, and the first systems that were discovered were these systems where the A cation, which would be calcium in an inorganic system, is replaced by a simple amine like methylammonium. And so the one that many of you will have heard of is the methylammonium lead iodide, which people are studying for photovoltaic applications. There's also an additional extension of this concept where not only do you replace the A cation with an amine, but you replace the anion with an organic anion like formate. And so you have both sort of organic cations in the A cavity, but also organic linkers as well. And this is a very large family, actually. So whereas with the inorganic ones, the hybrid sort of iodides and so on, simple systems like this, you can do the same thing with azides, but there are formates, there are cyanides, there are dicyanamides, there are borohydrides, and so on. So it's a huge and growing family. And in fact, we just published a review on the topic with my sort of former co-worker Wei Li and other colleagues that summarizes everything you could want to know about this large and growing family of hybrid perovskite materials. So the first thing that we did in the halides area just recently was to look at the application of the Goldsmith tolerance factor, which was developed in 1926 by Goldschmidt and applied to simple inorganic perovskites. And using the radii of the different cations and anions, you can calculate a tolerance factor. And when the tolerance factor lies between about 0.8 and 1.0, then you expect to get a simple perovskite structure. And I always find this is amazing, by the way, that Goldschmidt could do this in 1926, and it was only about 10 years after powder X-ray diffraction was first demonstrated. It's just sort of extraordinary, the rapidity with which he was able to apply this to rather complex structures. What we did was to extend that to the idea of the hybrid systems, and this involved two steps. One is to assign effective radii to the organic cations, to the alkyl ammonium cations, and secondly, to assign sizes to the organic linkers as well, such as formate. And we have to treat those as a cylinder, so we have not only the radius of the cylinder, but also a height for the cylinder. So we introduce an additional parameter here, which is the height of the cylindrical anion. And we did that for a very large number of combinations. And there are two papers on this, but basically we calculated about 2,400 tolerance factors for different combinations of cations and anions, and about 700 of them have tolerance factors in the window where you would expect a perovskite. And of those, about 140 of them are known. Now, lots of them will never be made, probably because the chemistry is very difficult or the tools are too approximate. But it does actually work rather well for the known system. So this blue line here shows you the calculations for the alkyl ammonium lead iodides with different cations, and this band here is the perovskite region, and the ones that are known are numbers 3 and 6 there. And then we did the same calculation for the formates, and again the solid green squares here are the ones that are known to be perovskite. So there are rather more perovskites in the formate family than there are in the iodide family. If the cation's too small, like the A cation, if you have ammonium, then it falls well outside that range and you get other types of structures. Whenever you're at the margins, close to 0.8 or close to 1, then you're likely to face polymorphism questions. And that happens in the case of, if you take hydrazinium zinc formate, and this forms both a perovskite and a channel type structure, which is shown on this right here. The left one is the perovskite. I just wanted to show you this. It's something we did last year, but now with modern DFT calculations, you can calculate not only the global minimum energy, but you can also, using lattice dynamics, calculate the entropy as well, the vibrational entropy of the system. And with the vibrational entropy, you can then calculate the free energy. And so what we're able to do is plot the free energy of the two systems as a function of temperature and show that there's a crossover at around room temperature. So it's possible to say not only which is the most stable polymorph, but under what conditions would you expect one to transform to another. And one of the simple rules of thumb that comes out of this is that the low-dimensional structures, like the hexagonal channel structure, have higher entropy, so they're more favorable at high temperatures. And the global minimum tends to be the classical perovskite structure. So one of the reasons we went into the halides area is that for the last decade or more, we've worked on perovskite formates, and there are very close analogies. So, for example, this dimethyl ammonium manganese formate is a classical example, and it's a very interesting system. It's a ferroelectric, below about 160. It's multiferroic if you have a transition metal like manganese, because it also orders magnetically. And there are a lot of interesting physics questions there that we continue to work on. You see glassy behavior due to the freezing of the methyl rotations at very low temperatures. And one of the things that we found is that as you change the alkyl ammonium cation with either more or less hydrogen bonding, then you can use that to tune the mechanical properties of the systems. And we've extended that into the halide systems as well. Well, the halide-based solar cells probably need no introduction, but it's been fantastic development. Of course, it was with Kojima et al.'s paper in JAX in 2009 was the initial breakthrough here, showing that you could use this methyl ammonium lead iodide as the active layer in a solar cell. And at that point, it had an efficiency of about 4%. Over the last 7 years or so, that has grown to more than 22%. And there are really only two major systems that people have looked at here. One is the methyl ammonium lead iodide, which is the classical one. And then the other amine cation that you can use is this formamidinium cation. I'm showing it here. It's kind of related to formic acid in a way. It's the sort of amine from formic acid. And those two cations, which are known as methyl ammonium and formamidinium, are the key systems that people have worked on. You can use bromide instead of iodide, but of course the band gap gets bigger. And this is what has excited people, that this is just a little bit from the NREL efficiency chart, and this red line here is the improvement in the performance of the methylammonium lead iodide related systems since the paper in 2009 in JACS. And so you can see it's sort of reached over 22%. It's nearly as good as silicon now. And the reason this is very exciting is that these systems are solution processable and they're easy to make. And so it has all the advantages of an organic photovoltaic in a way, and some of the problems of organic photovoltaics. But at the same time, the efficiency is probably twice as good in a laboratory as you could ever get with an organic photovoltaic system. So that's the reason there's so much excitement about them. Now, we've done a variety of things because we were interested in the role of hydrogen bonding in the formates. We've been looking at the role of hydrogen bonding in these halide systems, and we looked specifically at the methylammonium lead iodide and mapped out the energetics using density functional theory, mapped out the energetics of the methyl behavior. And what happens in the methylammonium lead iodide, as in many perovskites, is that at high temperatures you have a cubic structure, simple cubic structure. As you cool it down, the methylammonium cations, which are disordered in the cubic structure, become progressively ordered, and there's a series of phase transitions. It becomes tetragonal, it's tetragonal at room temperature, and then it becomes orthorhombic as the cation orders. And so we've studied that process using DFT calculations. The reason this is important is that the band gap is controlled in part by the tilting of the octahedra. So the octahedra don't necessarily line up kind of linearly, but they're tilted in most perovskites. And that's the case here. And there's, as you can see here, there's a relationship between the band gap on the one hand and the tilting angle of the octahedra. So the more linear the bonding between the octahedra, the smaller the band gap. So if you have large tilting, that makes the band gap increase. So one of the questions is what controls the tilting? And we've looked at this with Jung-Hoon Lee, who was a postdoc with me, he's now at Berkeley, and some of my other colleagues, looking at the different factors that control the tilting in these systems. And there are basically three factors. One of them is the size of the A cation. So you see a correlation between the A cation size and the tilting. The second is the hydrogen bonding that I was just mentioning. And the third is the role of the lone pair, because the lead is in the divalent state. So technically it's an S2 ion. And so the lone pair and the lead iodine bonding is important in controlling the tilting and therefore the band gap. And you can see these different curves show how you can have, for different families of materials, you can have the same, this doesn't show it properly, the same tilting angle, but you'll get different band gaps. So the amines are not entirely advantageous because the amines with the hydrogen bonding give you more tilting, and that tends to make the band gaps wider. So the stuff that we've been doing very recently has been on formamidinium lead iodide, and unlike the methylammonium one, this is not very well understood as a function of temperature. So we've been looking very carefully at the crystallography as a function of temperature. It undergoes a phase transition like the methylammonium one does, but this is a very frustrated system with formamidinium. And so we're able to, we've determined the structure of the first ordered phase. We know that there's a second ordered phase at lower temperatures, and the system's so horribly twinned, which is quite common in perovskites, that we're unable to determine the structure fully. But we have a phase transition just below room temperature from a cubic to a tetragonal system, And we're able to pinpoint the location of the methylammonium cation, which is partially, not methylammonium, formimidinium cation, which is partially ordered at that point. And we've also done first principles molecular dynamics simulations to look at the behavior of the cation as well. In addition to getting ordering with cooling, you also get a phase transition on applying pressure as well. So we've done single crystal synchrotron X-ray diffraction work on this. And again, there's a phase transition. It's a very low pressure. It's at about 0.2 GPa. So even very low pressures will give you a phase transition to the same tetragonal structure that you get on cooling. And we're able, computationally at least, to follow the change in the band gap as a function of pressure. And it shows interesting things. First of all, with pressure you get more tilting, and that makes the band gap go up. And then at some point, the more classical trend kicks in, where as you pressurize a system, the overlap integrals get better, and so the bands broaden, and so the band gap goes down again. So what's interesting about this is that the transition is at such low pressures, is that this is the kind of thing that could happen if you were processing the material to make a device, for example. So you can't be sure that the normal ambient pressure phase is the one that you're dealing with. Okay, here's the problem. Nobody wants to launch a new technology around lead. And like if you went to Mitsubishi Chemicals or Sumitomo Chemicals, they will not be enthusiastic to launch an entirely new technology around using lead. For the last couple of decades, people have been trying to make lead-free ferroelectrics, and so people are not anxious to develop new technology. I think there is zero probability that this would be commercialized in Europe, for example, using lead. So what we have to do is find materials that are free of lead, but capture the same physics in terms of light harvesting and charge transport that you get in the lead phases. And that's difficult. Tin looks quite attractive because it's non-toxic, but the tin phases have much wider band gaps, so that's an issue. And so other questions we might want to worry about. First of all, do we really need a perovskite? Or could we use more or less any structure? And I think you don't need a perovskite, but what you do probably need is a system that's three-dimensional, because low-dimensional structures effectively give you much bigger band gaps because they're quantum confined. So they behave like quantum wells if they're two-dimensional. And then another good question is whether you really need a hybrid phase for the solution processing, or could you reasonably use a phase where you'd have, instead of the alkyl ammonium cation, you could use an alkyl metal, alkaline metal. And I'll show you some examples of that briefly. So we decided at an early stage that bismuth was a good way to go. So we've been thinking about this for a couple of years. And the reason for that is that bismuth's next to lead in the periodic table. It captures most of the same physics. It has a different valence state, which makes life difficult. So bismuth is bismuth 3+, but it's isoelectronic with lead. And you can't make the simple bismuth perovskites because of the charge issues. But if you do look at iodides, then, for example, you can make, and this is one that we discovered, you can make ammonium bismuth iodides, which are, it has a layered structure. It's kind of unusual layered structure. So it's not a perovskite, but it's kind of related to perovskite. It's deep red in color, so it's got a band gap of about 2 eV. We really want a band gap of, say, 1.5 to do this rather than 2 eV. So this is interesting, but it's not probably the solution to the problem. We've been looking at double perovskites, so this has been a big trend. can you replace two lead cations with a univalent cation plus bismuth 3+? And actually, there are quite a lot of systems that have been known in the past, like this first one here. This was Norman Edelstein at Berkeley in 1970, making cesium double perovskite halides, chlorides, and then other people like Hema Karunadasa at Stanford, it's published on the cesium ones, and also Pat Woodward at Ohio State as well. So what we've been doing is exploring, can you make a hybrid double perovskite? Since none of these were known when we started our work, so can we use ammonia or sort of real hybrids like methylammonium and so on to make a double perovskite? And we've had a certain amount of success. My co-worker Wei-Feng Xia has done this, and the first one that she made was this methylammonium potassium bismuth chloride. If you were going to make one, this is the least exciting possibility, but it's the one that we managed to make first. And it's got a rhombohedral structure, so it's got a nice ordered structure. And we determined it with single crystals, but we can make it nicely pure. Not surprisingly, it's got a huge band gap. So it's got a band gap of about 3 electron volts. It's an indirect band gap. And it's not very interesting for photovoltaic applications, but it turns out to be very interesting for photoluminescence. So we're doing work with Richard Friend's group in physics on the photoluminescence of it. And using this structure, since we know the rhombohedral structure now, which is well ordered, that makes it easy to do DFT calculations on other analogues. And so we've done that for all of these combinations for chlorides, bromides, and iodides, with bismuth in combination with things like copper, silver, thallium, potassium. And all of these are stable in the calculations, and some of them, such as the thallium bismuth iodide and the silver bismuth iodide, are predicted to have very low band gaps. Obviously, the band gaps are not reliable from DFT calculations, but the trends are clear, and you know in which direction you should be doing the chemistry. And so the second one that we made was the thallium phase. So you'll notice that this is isoelectronic with the lead phase, since thallium and bismuth are on each side of lead in the periodic table. It's a bromide. It has a direct band gap in this case at about 2 eV. And this is a neat system. It doesn't solve the problem. Nobody wants to solve the lead problem by using thallium, which is even more toxic. So it's interesting as a model system to compare with the lead phases, but it's not something that we're going to spend a lot of time working on. So we've done DFT calculations and UV visible spectra and so on, looking at the band gap. And then the most recent one that we've done, which has just been published, is this methylammonium silver bismuth bromide. So this is the first sort of really interesting looking one from the perspective of the toxicity and getting around the toxicity. And this is difficult to make. All these things are difficult to make. It's dead easy to do the calculations, but when you're in the laboratory, just because it's stable in the calculation doesn't mean that you can make things. And to do this, for example, you have to do it using a seed of the methylammonium lead bromide. And there's no lead in the final product, but nevertheless, we've been unable to make it without using a seed to get the crystallization going in the right direction. And we've sort of done the sort of full characterization of the system, and we're currently doing some work with our colleagues in physics on the sort of device types of properties. One other thing in parallel with all this, my student Shijing Sun has done a lot of work on mechanical properties. So we've looked at the mechanical properties with nanoindentation on single crystals of the lead phasers for chloride, bromide, and iodide. Of the formamidinium, formamidinium is more compliant than the methylammonium, so this is unpublished. And we've done the mechanical properties of the double perovskite systems we've made, and those again are more compliant than the lead phasers. So having two cations gives you a more sort of flexible structure. So just to conclude, key things are that we have managed to make the first hybrid double perovskites, which has been a big achievement. We don't send these things off to science and nature, which is so slow because the field moves so fast and you don't want to be the second in it when you've made it. So we send them off to journals where we can get them published quickly and also put them on the archive. And they've got very similar properties to the lead analogues, but for the most part they've got indirect band gaps, which is a disadvantage, but they have better thermal stability, smaller Young's moduli. So far there are no hybrid iodides. Nobody's reported any hybrid double perovskites other than the ones I've shown you, and there are no iodides reported at all, therefore. There are one or two inorganic iodides, like this cesium one, which is looked at for gamma ray detection. And we've begun to do device measurements on them. And our targets are really band gaps of about 1.5 eV for the solar application with a tandem cell, and about 2.75 for the wider band gap systems for blue emission. So we've worked with lots of people. I didn't talk about the resonant ultrasound spectroscopy, but these are people that we've worked with in different parts of the work, especially our colleagues at Singapore who made large crystals of the lead phasers for nanoindentation. And I should mention Satoshi Tominaka, who did conductivity measurements, who's here working at NIMS, but spent a couple of years with me in Cambridge. And on that note, thank you for your kind attention.